Welcome to CS 350. This is Karthik Gopalan. In this lecture, we will learn about concurrency. Specifically, we will focus on the topics of race conditions and deadlocks. So let's first look at various execution models that you might use in a computer system. The simplest execution model is the sequential model. Let's say you have two tasks, task 1 and task 2. Using the sequential model, you will first execute task 1 to completion, and then you will switch the processor to task 2 and execute task 2 to completion. So you don't switch between task 1 and 2 as you execute. So basically we execute each task sequentially till it finishes. The second execution model is called the concurrent execution model. In the concurrent execution model, we have a block of time and we switch our attention between multiple tasks during that block of time. So in this example, let's say we have one CPU and two tasks. Now we switch between task 1 and task 2 during a given block of time. So we say that task 1 and task 2 are making progress concurrently within a given time window. The third execution model is the parallel execution model. In fact, parallel execution model is a subset of the concurrent execution model. Parallel execution model is applicable only when you have more than one CPU in a system. So here we have two CPUs and each CPU is dedicated to executing one task. So we execute task 1 in CPU 1 and task 2 in CPU 2. As a result, we say that task 1 and task 2 are executing in parallel. What that means is that task 1 and task 2 are executing together in real time. They are making progress together in real physical time. Hence, we call this a parallel execution model. Obviously, if you reduce the number of CPUs to 1, then it becomes concurrent but not parallel. So parallelism is a form of concurrency, but not all concurrency is parallelism. So sometimes when there are multiple concurrent tasks, these tasks may need to talk to each other. In other words, they have to communicate with each other. This communication may be either by exchanging data or by coordinating with each other by sending each other some signals. So when multiple tasks need to talk to each other, then we need primitives or special support from the operating system to support such communication. Particularly, we need access to shared resources by multiple tasks. For example, the shared resource between two processes or two threads may be in the form of signals, pipes, or shared memory. If you're using threads, then of course everything in the address space of a process is shared between the threads. However, if you're using separate processes, then you may need to set up special inter-process communication objects by requesting the operating system through system calls. An important concept in concurrency is the notion of a critical section. Critical section refers to any piece of code in a concurrent task that modifies or accesses a shared resource, a resource that is shared with another task. For example, if two processes are modifying a piece of shared memory, then any code that accesses or modifies the shared memory is part of a critical section. So, or you might, for example, have a linked list that is shared between multiple threads within the same process. And if multiple threads are modifying this shared linked list, then that code which modifies the linked list constitutes a critical section. So the notion of critical section also brings in two related concepts, race conditions and deadlocks. When you have critical sections that are modifying a shared resource, then if the two or more threads or processes, they don't talk to each other when modifying the shared resource, then they might lead to incorrect behavior. For example, if you have a location in shared memory that is concurrently updated by multiple threads, then one thread may override the results of another thread, and this may lead to incorrect output from the program. Or if you have a linked list and let's say one thread updates the linked list while the other thread is trying to read from it, then it might lead to incorrect pointers and lead to the crashing of the program. So race correct condition is basically incorrect execution of the program due to lack of synchronization between multiple threads. On the other hand, you have a different situation called deadlocks. In this case, you might have multiple threads that synchronize with each other, but they may be doing the synchronization incorrectly. So as a result, you may end up in a situation where one thread depends on another thread, which then depends on another thread, and so on. And you may end up with a cycle where multiple threads end up depending on each other and nobody makes any progress. So essentially all threads or all processes in a deadlock are basically waiting for each other and nobody makes any progress indefinitely. So we will first start by examining race conditions and how to overcome race conditions, and then we will look at the problem of deadlocks and how to solve deadlocks. So the general solution to race condition is called mutual exclusion. Mutual exclusion means that if two or more processes or threads are accessing a shared resource, then don't allow them to execute in their critical section at the same time, or don't allow them to execute in the critical section concurrently. As an example, we have two processes, process A and B. Both of them want to access a shared resource. First, process A starts modifying the shared resource, so it enters the critical section. While A is in the critical section, then at time t2, B attempts to enter the critical section to modify the same resource or to access that resource. At this point, B is blocked. It's not allowed to enter the critical section. Rather, B waits. And B will wait till A leaves the critical section at time t3. At time t3, B is woken up and it is allowed to enter the critical section. B then enters the critical section, accesses the shared resource, and leaves it. So, in order to enforce mutual exclusion, the general sequence of actions is that before entering the critical section, a process or a thread must acquire a lock that guards the shared resource. Next, once it is able to successfully acquire the lock, it can execute the critical section. And finally, once the critical section has been executed, the thread or the process should release the lock. Now, since during the time that lock has been acquired, no other process can enter its critical section to modify the same resource, so the length of the critical section should be bounded and generally it should be small so that other processes don't have to wait for a very long time. There are generally four conditions to for correct mutual exclusion. The first condition is that no two processes must be simultaneously in their critical region or critical section. This is enforced by appropriate locking. The second condition is that there should be no assumptions made about the speed or the number of CPUs. For example, one process should not assume that the second process would leave the critical section at a certain time. Different CPUs may have different speeds. Even if they have the same speed, different processes may make progress at different speeds. So it is important that the programmer not make any assumption about the relative speeds of different CPUs in the system, or make any assumption about how many CPUs are there in the system. The third condition is that if one process is in the critical section, then it should not be blocked by some other process that's not accessing the shared resource. So so as a result, we want to ensure that if a process is outside a critical region, it should not block some other process which is inside the critical region. This is important because you don't want dependencies between processes to extend to others who are not accessing the critical resource. The fourth condition is that no process should wait forever to enter its critical region. The amount of time required to enter the critical region should be bounded for every process. Conditions 1 and 2 are generally enforced by the operating system. If operating system provides locks to guard a critical section, and as long as programmer uses those locks, the operating system should guarantee that two or more processes don't end up in the critical section at the same time. Conditions 3 and 4 are generally programmer's responsibility. The operating system cannot enforce these. So basically the programmer should guarantee that no third-party process blocks a process that's already in a critical section, and that the length of the critical section is bounded. Operating system cannot guarantee the boundedness of a critical section's length. If you consider the concurrently executing processes as readers and writers of a shared resource, then there are certain rules of thumbs that are generally applicable for mutual exclusion. So in this example, let's say that you have a linked list and one thread may be updating the linked list, for example, adding items to the linked list, and the other thread may be simply traversing the linked list from the beginning to the end. So we obviously don't want the linked list pointers to be modified by one thread while another thread is traversing it. If you generalize this concept, we can derive a table as shown in the figure. Here we give an example with two threads, but you can extend this principle to any number of threads. So if you have thread 1 and thread 2 that are reading from a shared resource, such as traversing the linked list, then you can allow simultaneous traversal as long as the threads don't modify the linked list. So multiple readers on a shared resource is generally allowed, and this does not need to be guarded by a lock. However, if you have a possibility that one thread may be reading a shared resource while another is modifying that shared resource, then this should not be allowed. As long as there is at least one writer to a shared resource, all other threads or processes must be disallowed from entering the critical section. So the same rule applies if you have two threads, thread 1 and thread 2, which are both writing to the shared resource. In some special situations where the programmer understands the semantics of multiple readers and writers, you might allow multiple threads to be in the critical section as long as the programmer guarantees that they don't end up with incorrect execution. For example, some lockless data structures may allow multiple threads to access a shared resource concurrently. So now we will look at different types of locking mechanisms. The most simple locks are called blocking locks. In a blocking lock, when a thread tries to acquire a lock, and let's say that the lock is not available, then the thread gives up the CPU to other threads and waits for the lock to be available. So in terms of pseudocode, you might represent this behavior as a while loop in which the thread checks for a lock, and if the lock is unavailable, it gives up the CPU. When it wakes up again, when it gets control of the CPU again, it checks for the lock again, and so on till finally the lock is available. At that point, when the lock is available, the thread claims the lock and returns success, and then the thread can enter the critical section. So in this example, the blocking by a thread on a lock can be unbounded. There is no fixed amount of time within which a thread is guaranteed to acquire the lock. But the usage of such locks is very simple. The caller simply calls the lock operation on the shared resource. Once the lock is acquired, he executes the critical section, and once the critical section is done, he unlocks the resource and exits from the critical section. So in this example, the lock operation always succeeds, even though it may take a very long time to succeed in some cases, but the lock operation is guaranteed to succeed eventually. On the other hand, the disadvantage is that the locking operation may block indefinitely. What that means is that a process would be moved out of the running state into blocked state. It would be woken up again when the lock is available. At that point, it would move to ready state, and finally it will move to running state. The process will move to running state. There in running state, the process will try to acquire the lock again, and if it is successful, then it can enter the critical section. So moving from running to block to ready and then back to running, this will take quite a bit of time. This is a high overhead operation that may involve multiple context switches between the various processes. So blocking is preferable only if you expect the lock to be taken for a long time. However, if the lock may be soon released by another thread, then it may be too much of an overhead to go through these cycles. So we will look at some other alternatives in the next couple of slides on what you can do if you do not want a thread to block. So the second form of locking is a non-blocking lock. So with the non-blocking lock, a thread will try to acquire a lock. It will check if a lock is available. If the lock is not available, then it will simply return back to the caller with a failure. And if the lock is available, then it returns back to the caller with a success. So in this example, there's no blocking. Either the thread acquires the lock or it doesn't and returns back with a failure. So such form of locking is sometimes known by the name try lock. The usage of try lock would be as follows. The caller would call try lock on a shared resource. If try lock is successful, then the caller would execute the critical section and finally unlock the resource. If the try lock fails, then the caller does something else. So caller should have a backup plan available to handle the failure of locking. What if the locking fails? Then what do you do? So the advantage is that there's no unbounded blocking of the process, but the disadvantage is that the caller needs to have a plan B, a fallback option to handle the locking failure. The third option is to use spin locks. In the case of spin locks, we don't want the process to block, but we also don't want the process to fail on acquiring a lock. So in this case, while to perform locking, the caller would check for a lock, and if it is not available, then instead of giving up the CPU, the caller goes back again and checks for the lock again. So basically in a tight while loop, we are constantly checking for the lock until it becomes available. If you think of the lock as a memory location whose value is 0 or 1, if 0 represents available lock and 1 represents an unavailable lock, then then while the lock is unavailable, the caller will be stuck in the while loop. Once the lock value becomes 0, then the caller would return from the while loop, and at that point he would return success to the caller, and at that point the caller can execute the critical section. So usage of spin locks is as simple as using blocking locks. You call spin lock on a shared resource, then you execute the critical section once spin lock succeeds, and then you call spin unlock on the shared resource. The advantage is that if you expect the lock to be released very quickly, then spin lock is very efficient. Unlike blocking locks, spin locks don't have to take the process through the cycle of releasing the CPU, going to ready state, and then going back to the running state. So there are no context switches involved as long as the lock is acquired very quickly. On the other hand, the disadvantage is that if the CPU is expected to be held for a long time, if another thread executes in the critical section for a long time, then a caller can be spinning for quite a while on the CPU, burning CPU cycles. So this is really bad if critical sections are long. Essentially, you're wasting CPU cycles without making useful progress. Also, spin locks work efficiently only if you have more than one CPU. If you have multiple CPUs, then one thread could be spinning on the lock on one CPU while another thread could be making progress on the critical section in another CPU. If the system has only one CPU, then using spin locks is counterproductive, because if a thread is spinning on a CPU, on a lock, then the thread actually holding the lock cannot make progress on the critical section. So you have to be careful to use spin locks only on multi-CPU systems. In fact, implementations of spin lock often check whether there are multiple CPUs in the system. Otherwise, spin locks may default to blocking locks. In general, there are a couple of best practices for locking. The first is to associate locks with shared resources rather than code. A common mistake that many programmers make is that they would associate locks with pieces of code or critical sections rather than the resource itself. So, for example, if some code is manipulating a linked list, then you would want to acquire a lock on the linked list, not on the function that inserts or removes objects from the linked list. The second best practice is that if you have multiple shared resources, then have a separate lock for each shared resource. So let's say you have two linked list 1 and linked list 2, then you should have a separate lock for linked list 1 and another lock for linked list 2. This way, a process that only wants to operate on one shared resource can acquire only the lock related to that shared resource. If, on the other hand, you need to manipulate multiple shared resources in a single critical section, then in the critical section you'd have to acquire all the locks for all the shared resources before you enter the critical section. So for example, if you're moving items from one linked list to another, then you want to be sure that you have the locks for both linked lists before you start moving items from one linked list to another. Again, these properties are up to the programmer to enforce. Operating system cannot automatically enforce these properties. They don't necessarily lead to incorrect programs, but they may lead to inefficient programs. Now let's take a look at the problem of deadlocks. Deadlocks happen when two or more processes they stop making progress indefinitely because each process depends on some other process to make progress. Essentially, all the processes end up in a cycle waiting for each other and nobody makes any progress. So here's an example of two processes that end up in a deadlock. Here you have two processes, process 1 and process 2. They need access to two locks, L1 and L2. Each lock is presumably guarding a separate shared resource. So process 1 acquires lock 1 first, and concurrently process 2 acquires lock 2. Now process 1 tries to acquire lock 2 and it blocks. Why? Because process 2 is holding lock 2. So process 1 cannot acquire lock 2. On the other hand, process 2 tries to acquire lock 1 and process 2 also blocks because it can't acquire lock 1. So process 1 and 2 are in a deadlock. Process 1 cannot make progress till process 2 releases lock 2, and P2 cannot make progress because until P1 releases lock 1. So both will wait indefinitely. So the best way to prevent avoid a deadlock is to write code that guarantees there will be no deadlocks. Once a deadlock happens, it's almost impossible to end the program correctly. So solution to locking is called lock ordering. Lock ordering means that if you have to acquire multiple locks to enter a critical section, then all the participants in the concurrent system should acquire the locks in a fixed order. So let's say our fixed order is lock 1 followed by lock 2. So in this example, we must enforce, rather the programmer must enforce that both processes acquire lock 1 first and only then they acquire lock 2. So going back to the previous example, if both processes follow lock ordering, then P1 would acquire lock 1. At that point, P2 will also try to acquire lock 1 concurrently, but it would block. Then, since lock 2 is still available, P1 can go ahead and acquire lock 2. P1 can execute the critical section. All this while P2 is blocked, trying to acquire lock 1. Once P1 is done with the critical section, P1 releases lock 2. Then P1 releases lock 1. Again, note that you don't have to release the locks in this particular order, but it's desirable to avoid certain inefficiencies in the concurrent system. And then finally, once lock 1 is released, P2 will be woken up, then P2 can acquire lock 1, then it can acquire lock 2, and then P2 can execute the critical section. So as a result, both P1 and P2 make progress without any deadlocks. The very simple rule we followed was that both processes had to acquire L1 before they tried to acquire L2. Now this is just a problem with solution with two processes and two locks, but you can very easily extend this solution to multiple locks. So when we generalize the lock ordering solution to multiple locks, you may have n locks L1 through Ln and k processes P1 through Pk. Any process can acquire any subset of locks to enter a critical section. So note that all processes don't have to acquire all the locks. A process may choose to acquire only some of the locks. But whichever locks are acquired, they have to be acquired in the order that is agreed upon ahead of time between these processes. So as an example, let's say that you have two processes Pi and Pj. Pi acquires locks L1, L5 and L10. Pj acquires the locks L1, L3 and L10. These are allowed because both Pi and Pj are acquiring locks in the order in which locks are sorted. However, if there's a third process Pk, if it tries to acquire L5 and then L2 and then L1, then that is not allowed because P5 would try to acquire locks in an order that's not in the sorted order of the locks. So whichever subset of locks a process acquires, it has to be acquired in the order that's been agreed upon between different processes. A related problem to deadlocks is called priority inversion. Priority inversion happens when a system uses priority-based scheduling. If you recall, priority-based scheduling is when you assign certain priorities to processes, and then the process with the highest priority gets control of the CPU. The lower priority processes have to wait till higher priority processes give up the CPU. So let's say you have three processes: PH, a high priority process, PM, a medium priority process, and PL, a low priority process. So to illustrate priority inversion, let's say that PL and PH need access to a common shared resource, which means that to access the shared resource, they must acquire a lock L. So it so happens that PL acquires the lock L first, and PL starts executing in the critical section. Okay, so now PH, which is executing concurrently, it wants to access the shared resource, so it tries to acquire lock L, but L is already acquired by PL, so PH has to block. So already we have a situation where a high priority process is blocked waiting for lock to be released by a low priority process. This itself is not a problem as long as PL exits the critical section successfully. However, it may so happen that PM, which is a medium priority process, may become ready, and it will preempt PL from the CPU. Since PM has a higher priority than PL, PM can preempt PL. Now, it may so happen that PM preempts PL so often that PL, the low priority process, never gets to finish its critical section. So we have a situation where a medium priority process PM is executing, or even though it has nothing to do with the shared resource. So the medium priority process gets control of the CPU while a high priority process PH is waiting for the release of the lock on the shared resource. This is called priority inversion. The priority inversion here is that a medium priority process PM has control of the CPU while a high priority process is waiting. Now, the solution to priority inversion is also pretty simple. Whenever we notice that PL has acquired a lock that's needed by a high priority process, then the moment the high priority process attempts to acquire the lock, we can bump up the priority of PL to high priority, the same priority as PH. So what that means is that for temporarily, while PL is in the critical section, it would execute at the same priority as the highest priority process which is trying to acquire the lock. As a result, PL would be guaranteed that it will not be preempted by the medium priority process PM. So that way PL can make forward progress in the critical section and ultimately release the lock so that the high priority process can execute. So by bumping up the priority, that is by allowing PL to inherit the priority of the highest priority blocked process, you avoid the problem of priority inversion. The problem of deadlocks also shows up when we are using locks in the operating system. Specifically, operating system code can be invoked in many ways, but primarily in three ways. The first way is through system calls made by processes from user context. The second way operating system's code can be invoked is through hardware interrupts. When a hardware interrupt occurs, the CPU that receives the interrupt would stop doing whatever it's doing and it would execute an interrupt service handler. This is known as the interrupt context. And once the interrupt service handler finishes, the CPU goes back to whatever job it was executing. The third way is through exceptions. Whenever a process makes any error, such as a floating point error or a null pointer exception, then the execution hardware would raise an exception and a corresponding execution handler executes in the operating system. So we are mainly concerned here between the interaction between the user level context through system calls and the interrupt context through hardware interrupts or even through exceptions. So it may so happen that the interrupt context and the user context may share some shared resource. Often there is some sort of producer-consumer relationship between the user context and interrupt context. For example, in a device driver, you might have user context issuing IO requests, and in the interrupt context, the device driver may pick up these IO requests and issue them to the hardware device. So again, as we know in producer-consumer problem, we need to have locking of the shared resource and some form of signaling between the producers and consumers. However, interrupt context is a special context because interrupt context preempts the user context in order to execute an interrupt service routine. So let's say that you have a thread T that acquires a lock L in the user context. At that point, while thread T is in the critical section, an interrupt fires from the hardware, which then triggers an interrupt service routine of the same CPU. The interrupt service routine would preempt the thread T. So note that thread T has been preempted while it was in its critical section. At this point, the interrupt service routine may try to acquire the same lock L that is being held by the thread T. Now, if you were using a blocking lock, then it would block the interrupt service routine. This might sound harmless or it might sound normal, except that note that interrupt service routine preempted thread T while it was in its critical section. So thread T cannot make progress until the interrupt service routine returns back from the interrupt context. So now T is blocked waiting for the ISR to return, and ISR is blocked waiting for T to release the lock. And T cannot release the lock till it finishes its critical section. So here we have a deadlock between a user context and an interrupt context which are waiting on the same lock. So dealing with deadlocks in the interrupt context can be very tricky because the normal semantics of two concurrently executing threads or processes don't apply to interrupt service routines. So the simplest solution to avoid deadlocks in the interrupt service routine is don't perform any blocking locks in the interrupt service routine. So if you need to perform any blocking locking, or if you need to access any shared resource, defer accessing the shared resource till you return from the interrupt. The Linux kernel, for example, provides mechanisms called soft IRQs where interrupt service routines can defer certain work till you return from the interrupt context. At that point, uh, these deferred work can be executed in a regular thread context where locking is acceptable. If you must access a shared resource in the interrupt context, then you can use the try-lock version of lock, that is a non-blocking version of a lock instead of a blocking version. In such a case, if you use a non-blocking version, then there is a possibility that locking may fail if the lock is already held by a user context. So the interrupt service routine must have a plan B, a fallback plan to handle locking failure. The third solution, which is often used in operating systems, is to disable interrupts completely when a thread enters a critical section. So various versions of locks are interrupt disabling variants. For example, you in the Linux kernel, different locks may have the term IRQ save appended to the end of the locking routine. What this means is that once you acquire the lock, interrupts will be disabled temporarily till the critical section is over and the thread unlocks, gives up the lock. So, although this may simplify the problem of deadlocks, but it is not without cost. So, if you don't have any interrupts during the critical section of a thread, then obviously no interrupt service routines can execute and none of them can acquire locks causing a deadlock. However, the flip side is that if your critical section is very long and if you leave the interrupts disabled for the duration of a critical section, then you might end up losing interrupts from the hardware. So, and the responsiveness of the system or even the correctness of the system may suffer. Then there's a third solution which is to use spin locks. If you have a multi CPU system, and then you can use spin locks in the interrupt service routine. But note that spin locks are also a form of blocking locks in that they constantly spin on the CPU instead of releasing the CPU to some other thread. You can use spin locks in interrupt service routine as long as you have multiple CPUs in the system. So uh, an interrupt service routine on one CPU may be spinning on a lock, whereas another CPU may have a thread that makes progress on its critical section. However, if you do use spin locks, threads should still use interrupt disabling versions of spin locks. So in case a thread is running on a CPU and it holds a lock, then you don't want an interrupt to fire on the same CPU while it's going through the critical section for the same reasons that we discussed in the previous slide. So, so again, when using spin locks on multi-CPU systems, you have to be very careful to disable interrupts before you enter the critical section. This brings us to the end of the discussion about race conditions and deadlocks. In the next lecture, we will learn about semaphores and condition variables.